Unit 4.04, we're going to explain how to find trigonometric values for radian measures between 0 and 2 pi. That probably doesn't mean a lot to you now, but it will. So go ahead and take a minute to copy this down. First things first, we're going to look at the bicycle wheel, and then we're going to talk about something called the unit circle, which you've actually already seen, and we're going to talk about how it will be very helpful for us. So we're quickly going to just talk about this bicycle wheel. So imagine you have the bicycle wheel here, and here's the ground. And we have some point P on the wheel. And the question, of course, go back and read it now. It says, okay, imagine that you've traveled a certain distance down the road. How far would P have rotated? And the big thing that we've got to realize is that if P spins all the way around, if the wheel rotates all the way around, then what is the distance that the wheel had to travel? So if I imagine that this is the piece of the wheel that's touching the ground, imagine that P rotates all the way around. So that means that, think about P rotating here, all these pieces have to touch the ground as well. Okay, so let's fast forward to that point. So P now is on the ground. And so you think about it, all these pieces, right? All these pieces here had to touch the ground, right? So this piece right here is now somewhere up here, and all these pieces had to touch the ground. And as P keeps rotating, all those pieces continue touching the ground. So this is what's on the ground now. So these had to have hit the ground before, and we're a quarter past P. That's how much it already touched the ground. And so finally, when P gets to the very end, right, if you think about it, this is what's on the ground now. So all of these pieces had to hit the ground. And remember, we were already a quarter past P, so all of the wheel has touched the ground, which means that the distance, think about it, the distance you've covered had to be the distance around the wheel, the circumference, which is 2 pi 13 inches, or 26 pi inches, which if you think about it, it's a little more than 3 times 26, or a little more than 75, somewhere around 80 inches that you've traveled. So now that I have this good idea that, okay, look, if the wheel travels, if it turns 360 degrees, that means it's traveled a full circumference of distance. And we know that full circumference is 26 pi inches, which is about 80 inches. Okay, and that means that it's turned 360 degrees. Okay, so this is just like the clock question. Imagine that instead of turning traveling all 26 pi inches, it's only traveled 1 inch, which means that this point P here will have only, moved 1 inch. Only 1 inch of the wheel will have hit the ground. Okay, so this arc length here would be 1 inch. And so if you know, hey, in order to make a 360 degree turn, you had to turn 26 pi inches. Well, how much of those 26 pi have you turned? You've turned one of them. So what you're saying is, what's 1 out of 26 pi? That's the that's the amount of the 360 that you've turned. So I take that proportion and multiply it by 360, and I will get 360 over 26 pi degrees. Okay, and we'll just leave it like that. And then, so the question becomes, all right, well, if that's how many degrees you've turned when you've gone 1 inch, what about when you've gone 10 inches? Well, that's just 10 times 1, so now I have 360 times 10, which is 3,600 over 26 pi degrees. And I can do the same for 3 feet and the same for 7 feet, right? It's very helpful to know that if I've gone 1 inch, that's the number of degrees I've turned, right? 1 out of the 26 pi total that I could have taken in one revolution. And so that's the amount of the 360 degree turn that I've gone, and that's the number of degrees. Okay? So now if I think about radians, right, a radian is saying, look, if you've gone 1 radian, if you've turned 1 radian, then you've turned 13 inches, because that's 1 radius length. So in order for a distance of 13 inches, if you've traveled 13 inches, that means you've traveled 1 radian. Okay, so in this case, though, imagine that you've only gone 1 inch. How much of that 1 radian have you gone? Well, if a whole radian is 13 inches, you've gone 1 out of those 13, so you've gone 1/13 of a radian. All right, and then you multiply it by 10, because you've got 10 inches instead of 1, 10/13 of a radian, so on and so forth. Okay, go ahead and finish this out. Make sure that you have answered any questions that you need, and now we're going to move on. So we're coming to a very big moment in our study of, we're looking for, and I want us to remind ourselves what we're looking for. So remember we saw that graph that we created which looked something like this. And we said, hey, we want a function that will repeat values. It will have this periodic movement. And we noticed like a straight line won't work at all because it just kind of keeps changing value. And so we tried to think of something that we're familiar with which repeats itself. And you notice a circle has a repetitive sort of construct, right? If I follow around a circle, I will keep repeating values over and over again. And so we're moving towards just being able to understand a circle and kind of compute it in a way that create a function that kind of follows the circle around. And we can use that to model things that are repeating. And so I want to talk about whether it matters what kind of a circle we look at. So I drew an arbitrary circle and some degree theta, and this angle is created by these 2 rays that are going outward, okay? And so imagine that this were just 1 radian. So that would mean that the radius of this circle is r, right? And let me use purple here. The radius of this circle is r, and also the arc length around that circle is r. What happens if I draw a much larger circle? So let's draw a larger circle. Okay. Now the question is this theta, is this still 1 radian? So now let's take a look. Let's use a different color here. Let's use red. So now notice that the radius of this blue circle is much bigger, right? And also the arc length has gotten bigger, right? And so in fact, it's still maintained. The radius here is still the length of the arc. And so this would still be 1 radian, whether I'm using a huge circle to measure it or I'm using a small circle. And so as we talked about before, what type of circle would be most easy to work with? And that would be a circle where the radius is just 1. Okay, that's going to be the easiest for us to work with, because in this case, I know that 1 radian, right, is just an arc length of 1, because that's 1 radius. And so what we're about to do, we're about to start investigating the properties of the circle, and it's important that we understand why we're using a unit circle. We could use any circle, but it's going to be easiest if we use a unit circle, and you will see why. Okay, so we're ready to start investigating the circle. Remember why we're doing this. We know that the path around a circle will start to repeat itself, right? And if we think about it, right, the whole way around the circle, that's a rotation of 2 pi radians. So if every time I rotate 2 pi radians, I'll start to repeat myself. And that's what we wanted. We wanted a function that will eventually start repeating itself. And so we need to investigate what's a function that will give me points that are moving along a circle, okay, along points of a circle. And we just talked about that any circle will work. So we're going to look at the unit circle, and we have a way of talking about the rotations because we have radians. So radians are going to move around a circle. It doesn't matter how big or how small the circle is. It's always going to be 2 pi radians for a full move around. And this is the unit circle because it has a radius of 1 Okay? And so let's consider an angle. Just use this right here, and this angle is constructed using these two lines. And so it is always, the way it works, a positive angle always moves counterclockwise. And by the way, I should just note that right now you want to create this on your paper, so pause the video and do the best you can to make this really accurate. You're going to want to keep this. So it moves counterclockwise, and we always start, the starting ray is always along the x-axis, and then we just move counterclockwise. Okay, so this angle moves that way, and it is, we'll call it theta. And what I want to know, right, I want to know what are these points that are moving along the circle, because what I want is I want a function that will give me these points so that it will repeat. And so my question is, what is this point right here? How do I compute that point right here? And we'll just call that point A, comma, B. And so our goal is to find the A value and the B value. Okay? So I encourage you to pause the video right now and just think about some ways you could do it. All right? Just whatever seems to work, just create something that might help you move forward, but just spend a minute or two on it. All right, so the one thing I do want to note that I forgot to is that a negative angle will move clockwise, and it will also start from the x-axis. So if I were saying a negative, I've said negative, negative pi, or for example, negative pi radians. Pi radians is half of 2 pi, so that would be the angle starting here, moving negatively clockwise to right there. It'd be a straight line, it's 180 degrees. Okay, so I want to know, what is this point here? How do I calculate that point? Because if I can, well, guess what? These points move around in a circle. So after 2 pi radians of turning, all of a sudden I'll be back at that point, and it will repeat itself. So the first thing that I want to do is I want to create a right triangle right there. So here's my right triangle, okay? And the first thing that I want you to do is I want you to try and fill in as many sides of this right triangle as you can. You probably noticed that this hypotenuse has a measure of 1. Right? The radius of this circle is 1. You should be seeing why this is so helpful now. So this is a radius, and it is 1. Now, let's also think about what this side length will be. So to help us figure this out, let's just think about what the y value is, and that will tell us the distance, because we're moving from 0 in the y-axis up to some point. What is that going to be? Well, think about it. That's just the y-coordinate of this point here, right? So the length of this side is simply b. Okay? Once again, I'm moving upwards to this point from 0 on the y-axis, right? Up until I get to b, and that is the y-coordinate. So the side length here is exactly the length that will be equivalent to the y-coordinate of this point. And the same can be said for this side length. So this side length is exactly the x-coordinate of this point, right? If you think about it, you start in the x at 0, and as I move all the way out to here, this is where I get to the x-coordinate of this point. So if I were to move A in the x direction, B in the y direction, I would be getting to this point. And so this here, this side length, is A. And let me use a different color here. Let's use blue for A. Okay. And the question is, well, how do I figure out A and B? And what we're going to reintroduce now is sine, cosine, and tangent. So you may remember this. SOHCAHTOA. Right? Sine, cosine, and tangent. okay? So let's just pair back for a second and remember that we want to use the circle. We want to find these points on the circle. And what we know is that this point is what we get when we've turned some number of radians, this degree theta here. Okay? So we want to use theta. We want theta, our angle, to be the input to our function, and we want it to somehow tell us A and B. Okay? So let's just first consider what the cosine of this angle would be. Okay? Cosine of theta. Well, cosine is the adjacent over the hypotenuse. So try that out. The adjacent is side length A. And the hypotenuse is 1. And that is very nice, because that means that cosine theta is simply A. So cosine of our angle is the x-coordinate. Let's now try sine. So sine of theta, go ahead and try it yourself. Sine of theta is opposite over hypotenuse. The opposite of this angle is the B value, and the hypotenuse is again 1. So sine of theta is simply B, or the y-coordinate. So we have just discovered something incredibly useful. The point that will follow along the circle, the x value is the cosine of whatever the angle is that created the ray that intersected our unit circle. So this A value, whatever it is, no matter where I am, this is going to be the cosine of that angle. So we now know that the x-coordinate is the cosine of theta, and the y-coordinate, B, is going to be the sine of theta. And so now we can find any point we want by finding the cosine or the sine of that angle. Okay? And so we're actually going to redefine cosine and sine. No longer are we going to have to rely on sine being the opposite over the hypotenuse or the adjacent over the hypotenuse. What cosine is, and I'm going to go ahead and write this out. So the cosine of an angle theta is the x-coordinate where, and I want to be very clear here, where am I talking about? I'm talking about where this ray, and so if I'm thinking about an angle, it started at the x axis and it rotated out here. So this is what's called the terminal side of the angle. These are two sides of the angle. This here is the terminal side. So the cosine of theta is the x-coordinate where the terminal side intersects the unit circle. X-coordinate where the terminal side of the angle, I'll use this angle sign here, intersects the unit circle. Okay? And the same is true for sine. Sine of theta we can now think of as the y-coordinate. So go ahead and fill in the rest on your own. The y-coordinate where the terminal side of our angle intersects the unit circle. And this is great because now we know cosine theta and sine theta are going to be functions where when I plug in a radian measure, it's going to give me the point on the circle. And so what does that make tangent? Well, tangent of theta tangent of theta is the opposite over the adjacent. Well, the opposite is b, and the adjacent side is a. So I have b over a, and think about what that is equivalent to. Well, b is the y-coordinate, that's sine of theta, right? So tangent theta is nothing more than the sine of theta divided by the cosine of theta. So it's very important that you really understand how this works, because this is the basis for our functions, understanding the functions cosine and sine, which are going to generate the points along the circle, which are going to repeat themselves. Okay? And so go back, rewatch pieces that you need to rewatch, and tomorrow we're going to extend this. We're going to continue on using this method, and we're going to actually find some points along this circle.